All right, good morning, everybody. So today I'm going to continue on talking about arc-magmagenesis and what happens in the mantle wedge at subduction zones. And I'll preface this by saying, I'm an experimental petrologist by training. And so the view that I'm going to give you today is one that's fundamentally grounded in that work and that history of that work. And it focuses, therefore, mostly on major elements, but has some incorporation of trace elements. And so the view that I'm sharing is one in which we can then sort of compare and contrast with things that we know from other disciplines to see and ideally ultimately come up with a model that's consistent with all the different kinds of data that we have for rocks in subduction zones. So Adam Kent gave us a very nice lecture last week on building volcanic arcs, and he used this very nice slide from Richard's 2011 as his sort of fundamental cartoon to build off of, and he focused mostly on sort of what happens starting in the lower crust and to the surface in terms of talking about the genesis of volcanic arcs. And he sort of described the mantle processes as the raw materials for the factory floor. And so today the point is to focus on those raw materials. What are they? How are they generated? So the raw materials with which we're working are the part that we're focused on today. And this is how sort of Adam described them last week. He said, I'm just going to leave this for next week and leave it as this black box. So today I'm going to try to open that box and sort of investigate what's inside. And I hope that it's not Pandora's box, right? I hope that we're not sort of struggling with these demons that arise. I also hope that we're not experiencing the view of sort of petrology that Jeff described for us last week. Instead, I hope what we can do is we can do this, right? That we can make it a big box of fun here. So we'll see how we do with that goal today. So just to sort of start us off, if we look at a database, in this case I'm using a compilation of arc melt inclusions from arcs around the world. You can use other data sets. You could look specifically at volcanic rocks. They show a similar distribution here on what we call the Labost diagram, increasing silica content versus alkalis. And you can see that there's quite a wide range of melts basically found in subduction zones. And they vary from very sort of mafic picrobasalts and basalts all the way up through rhyolites and even more sort of alkalic things as we get up here. This is one way we can look at compositional diversity of things generated in subduction zones. And the question is really what produces this diversity? Another way we can look at it is by this famous diagram. And so I thought I'd continue on in the tradition of putting up sort of important figures in this work. So I gave you a lot of clues with this figure, if anybody knows what this figure is, about who this might be. Any guesses? Miyashiro, I heard someone say it, right? So it's Miyashiro-san, we should say, who developed this diagram as a way of thinking about the compositional diversity of magmas generated at arcs. And noticed that we see both calc-alkaline rocks, those that have a higher silica to iron over magnesium ratio, compared to tholeiitic rocks, which have this lower silica and higher iron to magnesium ratio. And so I put here in quotes sort of what's become the canonical way of thinking about this diagram is that those that are in the calc-alkaline field are ones in which have had some water involved in their genesis, and dry tholeiitic magmas are ones that tend to be drier. We'll talk about the nuances of this view today and how much it holds up, but this is sort of a classic way of looking at this diversity. And specifically today, because we're focusing on the mantle, we're focusing on these down here. these are the most primitive magmas that are generated in arcs. And when I say primitive, I mean things that have left the mantle with very little alteration on the way to the surface. So they haven't had very many crystals formed out of those liquids, and they haven't assimilated a lot of material on the way to the surface in the lithosphere or the crust. When you melt the mantle, and you have a melt that is still in equilibrium with the mantle, we call that a primary melt. But in reality, there's no way for a melt like that to make it to the surface without something happening to it. So everything that we actually see on the surface is a primitive melt. So these are all primitive melts, and if we do some small corrections to them to get them back to be in equilibrium with the mantle, they could then be primary melts. So today we're focusing on how do we produce these primitive melts at subduction zones, which presumably then give rise to the diversity of more silicic compositions that we see. And that's what that bubble says there. So we also know from a history of work starting back very early, sort of a fun anecdote, when the ring of fire as we know it was first discovered. It was discovered by a gentleman named Polvart. I'm going to mispronounce his name probably, but he dubbed it the volcanic girdle of the Pacific. So we've evolved a little in terms of what we choose to call it. I don't think that would have worked quite so well for Johnny Cash. But we now know that rocks, from studying those kinds of rocks ever since we first sort of discovered this relationship between the ring of fire or the andesite line or the volcanic girdle of the Pacific and rocks, we started to see that there were some associations of rock types, and we started to recognize that water played a role very early on. We know that from the petrology of the lavas just by looking at the minerals that make up the lavas themselves. Here we're looking at amphibole here in an andesitic rock here. We're also very familiar with the highly explosive nature of arc volcanoes, and the large part of that has to do with the volatiles that they release during their eruption, which are in large part H2O and CO2. And we know that from looking at melt inclusions. And here I'm showing a data set from Anderson in 1974 on Mount Shasta glass inclusions showing their water contents to the best ability to measure them at the time. So we've known for a long time that water played an important role in generating the magmas that we see at subduction zones. So we're going to try to mesh all of these bits and pieces going forward. And the main tool that we have at our disposal, like I showed you on that diagram, is these primitive magmas, these things that have made it to the surface with very little processing. And they, in fact, in their composition, store information about the temperature that they melted at, the pressure that they melted at, the bulk composition of the mantle that formed them, the extent of that melting of that mantle, and the type of the melting process. So they are really our, you can use whatever analogy you want. Our information capsule, our jewel to kind of get back to understand what's happening down here. And I like to show this picture. This is a very primitive basalt from Medicine Lake, a volcano in the Cascades. And if you can sort of focus in there, myself and Tim Grove are giving thanks to the mantle petrology gods for giving us this really beautiful primitive basalt with which we can study this. Yeah. So there's been lots of studies on what produces these primitive basalts. So this is a long history of work that goes back till, starting in the 60s really was the time we started doing a lot of this work. And there's been a lot of important work on it since then. And I thought I'd just sort of pick a point in time, and here I picked the early 1990s to sort of share where the debate was at the time on what produces primitive arc magmas. Those of you who are interested can go back and look at this nice paper by Davies and Stevenson in 1992, and their introduction provides a really nice overview of the debates at the time and all the key papers. So we have really nice examples of studies that show there's evidence for the slab, particularly oceanic crust eclogite melting to produce the range of compositions that we see in the literature at the time. There's nice studies that show evidence that you can produce this through decompression melting to varying extents. And that water is not always the crucial component. We have other nice studies, including this very famous book by Jim Gill, that to show that water fluxing the mantle can produce andesite and probably produces a diversity of andesites that we see at arc volcanoes. And we've also by that time learned that sediment and flux is a key player in producing the trace element variation that we see, and this is relating the sediment flux going in at the trench versus what we see in the arc volcanics. So we already, at this time, we're sort of debating, is there one model that fits all? These are all, there's a good evidence for each of these. And so that's sort of where we were, and I think I'm going to try to circle back at the end of the talk and sort of reflect on if we ask the same question today, where are we? So a lot of the work that I'm going to be sharing with you today is built off of our knowledge of how primitive magmas form through experiments. And when I say experiments, in my case, what I'm talking about are phase equilibria experiments that are done at high pressures and temperatures. And so to do that, we take a small noble metal capsule. In this case, I'm showing you a gold capsule. And we pick the capsule material in order to be relatively inert to exchange with elements with its surrounding, and also so it won't melt at whatever temperature we're interested in studying. And then we can either put a crushed up rock sample in it, or we can mix a synthetic mixture of elements. So we can take high purity silica, titanium, magnesium, put them together in the ratio of the composition we're interested in studying, and put them in the capsule. And then we put them in sort of a larger capsule called a pressure vessel, which then goes into this. This is a picture of one of the piston cylinders in my lab, which actually started its life at UCLA in the 1960s. So technology for piston cylinders and the barest death essences hasn't changed that much since we started studying these processes with them in the 60s. And so then we take all of these components, and essentially what we're doing is it's a giant vise. It's two hydraulic cylinders or pistons that are pushing against each other to pressurize the sample in the center, and there's a graphite furnace around the sample that allows it to come up to whatever temperature of interest. I have a nice little GIF that my student put together to show you all of the pieces put together, and there's water chilling and thermocouples to measure everything there. So we have all these bits and pieces, but in essence, when we're done, we have an experiment that looks like this. So this is the same thing we started with. This is the gold capsule that has now been deformed during the compression. And we now, instead of have this powder, we now have minerals and some fine wisps of melt in this case that have formed at that one temperature and one pressure while we were studying this one bulk composition of interest. And then we mount that up in here in epoxy in this case and polish the surface so that we can then analyze the composition of any minerals or melts formed. Here I'm showing a picture of an electron microprobe. We could do this also using analytical tools like secondary ion mass spectrometry to get at water contents, for example, or trace elements and things like that. So that's
out of the sample down there, on the left.
Yes.
Streams coming out of the sample.
This? Yeah. These are little wisps of melt, actually. And so the melt is, in this case, I have some nice pictures of this later, but in this case, this was a water-saturated experiment. And so when you quench that glass, instead of it just staying like a nice solid glass, the water exsolves out of it as you depressurize the experiment and essentially makes the glass the consistency of like beer foam. And so what you're looking at is that froth that's at the top, essentially, here. So, So we're doing experiments, and we're doing them at one temperature and one pressure, and then we're basically connecting the dots. We're making a phase diagram where we say what minerals are stable at each temperature and pressure that we examined, and where was their melt present. And so in this way that we can have lots of information about the variables at which the experiment was conducted, and then the relating compositions that arise from leaving that experiment long enough that we reach chemical equilibrium, i.e. steady state, that if we left the experiment for days longer, it wouldn't change anything. So these diagrams are all, in this case, for everything we're talking about today, constructed with the attainment of chemical equilibrium. And so we can take these kinds of phase diagrams and the compositional information of the minerals and the melts at them at a specific temperature, and we can use them to construct models of how mantle melting works. So I'm going to show you a bunch of diagrams like this, and I know that this is a lot of people's least favorite way of looking at things, but it's extremely useful, and I'm going to try to convince you why. So here it's what we call the Basalt Tetrahedron. And so imagine basically that I have minerals, so olivine, which is rich in iron and magnesium, has silica in it. Now I have calcium added to that assemblage, or here I have quartz, which is just silica, and here I have nepheline, which is essentially a mineral that's very low in silica, so it's the opposite end member here. By looking at rocks or melts plotted in this space, we actually can understand quite a bit of what causes them to vary in composition. And so what I'm showing you here is a 2D slice through this basalt tetrahedron. So here, for example, there's a red plane here that's slicing through one part of it, and a blue plane slicing through another part. In this case, we're looking at the olivine, plage, CPX, one. So we're looking at that red slice through the tetrahedron in this view that I'm showing you here. And so you could think of olivine being plotting over here, CPX would plot up here, and plage would plot up here. Now, if we melt this assemblage, our bulk composition before we melt it would be somewhere on here. That's as represented by if we were to take the assemblage and we were to convert it into the components olivine, CPX, and plage. And if we were to melt it, the first melt would appear here at what we call the eutectic. So that's a place where we have all the minerals plus liquid stable in the assemblage. And if we continue to melt it, it would move away from this eutectic depending on its bulk composition. It could move along this line here. So along this line, we have olivine, plagioclase, and liquid stable. It could move along this line where we have olivine, CPX, and liquid stable, or it could move along this line where we have CPX, plage, and liquid stable. And obviously then if we move off into one of these fields, we just have the mineral that's by this end member here and a liquid stable. So this turns out to be really useful for looking at how the composition of melts vary as we change intensive variables. So if I change pressure, the composition of this melt will move on this diagram, or where the location of the eutectic will move. So that tells me how, when I change pressure, or when I change temperature, or when I change water content, the composition of the melt varies. And then we can write a set of equations to explain that based on these experiments. So I'm going to just show you a little example of that. So here, this example that I was showing you was the location of the eutectic, or the location of the melt in equilibrium with olivine, plage, and CPX at 4 kilobars. Now I'm going to show you, so we're doing this on an undepleted mantle leurzolite, so a mantle that hasn't had a lot of melting, and it has all of the minerals stable. Olivine, it has a aluminous phase that could be plage, spinel, or garnet. It has CPX, OPX stable in it. So as pressure increases, if I'm melting this undepleted leurzolite, the location of that eutectic shifts downward on this diagram. So starting at 4 kilobars, and by the time I get to 10 kilobars, it's moved down here in this direction. And then I transition from plagioclase leurzolite into spinel leurzolite, and then so as I increase pressure, all of a sudden the vector with the direction that the melt composition is moving as a function of pressure changes direction and shifts shifts over in this direction here. So just the take-home message is, by doing experiments, we can identify how the melt composition changes and pick which variable we want to investigate. Do we want to investigate how the melt composition changes as a function of pressure, as a function of water content, as a function of FO2, for example? And we can make linear regressions, for example, of how that melt composition evolves based on that intensive variable.
Christy,
Yeah.
could you remind people what kilobars, megapascals
Conversion is?
Yeah,
Okay.
because us
Yeah,
geophysics people are
Yeah,
not
sorry.
used to kilobars.
So an easy way to think about it is 1 gigapascal, which is another unit of pressure, right, that we often use, equals 10 kilobars or 100 MPa. Okay, so that's the, did I say that right? 1,000 MPa, sorry. There's just a number of zeros added depending on which one you're using. 1 GPa, 10 kilobars, 1,000 megapascals. Okay.
I have one more question.
Yeah.
Is that path assuming a constant temperature, or is that assuming some kind of geotherm where temperature would increase from 4 to 20 kilobars?
So it's saying if we do an experiment at, I have another plot, I can show this in a little bit. If we do an experiment and we melt the same composition in each one, the melting temperature is a little bit different as a function of pressure, i.e. that's the solidus curve, right? But we're looking at in this case, we're looking at a fixed amount of melting above that solidus curve and how that moves. So you're looking at, say, constant, say 10% melting in each case.
How do you control that in an experiment?
How do I so we do, one experiment is at one pressure and one temperature, and then we'd say we would do the next experiment at another temperature but the same pressure, for example, or do it at, they do different temperatures at the same pressure. So you spend a lot of time doing experiments. You have to build big grids and tables of those PTX locations that you want to study, right? So this would be, probably, this is a assemblage of probably, say, doing 10 experiments at different temperatures to make sure that we figure out the melting extent at this pressure, and then this one, and then this one, and then this one, and this one. Yeah.
Just a really simple and quick question. You don't depend on composition at all, other than you just need all the minerals present?
Well, in this
does not matter?
So there are ways in which the bulk composition matters, and I have some figures to show that in a few minutes. But in this example, I'm using a fixed bulk composition that I'm showing you, so I'm not varying it at all. But we could do the exact same exercise now with a different mantle composition, which people have done, and show how these positions or this melt composition varies as a function of varying. Now we're melting a Hartsbergite mantle, or whatever, or we're melting a Lherzolite, but it has been variably metasomatized or something like that. Okay. So in the simplest sense, when we do these, right, this kind of thing that I just showed you, this is a way of understanding dry melting of the mantle. Because what we've just done is we've taken a mantle composition and we've changed pressure and temperature and seen how melt composition varies. So we have a fixed, in this example, bulk composition. We have not added water to it. So what we can do then is we can explain basically the range of primitive mantle melts that we see at subduction zones. We can, in this red field, we can simply get those by varying by dry mantle melting and variations in the temperature of melting, for example, or the pressure of melting. So this is a very simple, straightforward way to get primitive basalts that erupt in arcs of that composition. Any questions about that? Okay. So this is speaking to some of those questions we just had. So if we were to integrate, now we do lots of experiments, and now we're going to vary, for example, the pressure of melting, the temperature of melting, or the melt fraction of melting. We can explain, these are different names of different kinds of basalts that we see on Earth. We see olivine tholiites are sort of typical of what we get in mid-ocean ridge environments, especially these ones here. We can get things that are picritic. Sometimes we see those, for example, in ocean islands and other places. And so those, for example, we can get by simply getting much higher melt fractions at higher average pressures compared to MORB. Or we can get alkali basalts by melting at a higher pressure and low melting extents compared to MORB. And then we can also perhaps get bonanites at high melt fractions and low pressures. And quartz tholiites, which is a different version of a tholiite, by varying the melt fraction at a low pressure. So you can see that here, with just these three variables, we can explain a lot of the compositional variation that we see in dry, primitive magmas. And so this work has been relatively well established now, starting with people like Kashiro in the 60s and moving forward successively with many generations of experiments. And we have some very nice forward models. So it says, if I want to melt the mantle at this temperature and this pressure, what is the melt composition that I'm going to get? And I want to melt this bulk composition. We have some very nice models that allow us to do that. So this is an example one from Bain and Grove, which is a synthesis of a number of previous sets of them. So it covers a range of bulk compositions. And I'm showing an example for melting at mid-ocean ridges with this model. And so you can put in sort of your interest in bulk composition, and for example, and it's showing you here, here's the iron content as a function of depth for the melts that you would generate in a mid-ocean ridge environment, or the sodium content as a function of depth. So this is a forward model where you're just specifying the conditions, and we can predict the melt composition in this environment. And there's a number of these that sort of do this sort of calculation for us now, and they're reasonably good. I'm showing you here, I guess, a caveat, which is that each of them is sort of well-tuned or calibrated for their specific set of experiments and their bulk compositions. And here in Bain and Grove is a plot that shows some differences between different models. So they don't all give you exactly the same thing. So there's still some disagreement between them based on how they were calibrated and what their sort of main application is for. So here is an example. So Kinsler and Grove, that should say Kinsler and Grove 1992, not 2015, is a sort of melting model that was based on experiments that came out in the early 90s for mid-ocean ridge magmagenesis, and that's showing you the melt compositions that are here in the red lines. And then P-melts is another popular model for looking at mantle melting compositions that you can use as a forward model. And the curves that it predicts are shown here in black for composition as a function of pressure. And then Bain and Grove is comparing its models to both of these here. So you can see that if I were to use P-melts and I were to melt at 20 kilobars, and up here at the top is if I have 1% melt, and at the bottom is if I have 20% melt. I would get something, for example, that is much lower in silica using P-melts at 20 kilobars compared to that same calculation from Kinsler and Grove versus that same calculation from Bain and Grove. So there's still some questions about. We can compare these to natural samples, but we still struggle a little bit with sort of, Bain and Grove are proposing, we're doing the best job so far, but there's certain limitations and pros and cons to each model.
What's the reason, basically, why? What's the reason why there's such a big, huge difference between the Grove and P-melts?
So it has to
Are they oriented towards different objectives, or they use totally different methodologies, or?
It has to do with the data set that they're calibrated with, right? So they're all calibrated by a body of experiments that have been attempting to vary, certain parameters and then investigate the certain parameters, temperature, pressure, composition effects on the melt composition. And P-melts has been calibrated on, at the time it was calibrated, it had a much larger, shall we say, compositional pressure temperature box that it was trying to calibrate in, versus these, which were specifically, in the case of Kinsler and Grove, just trying to do a really good job with doing experiments on mid-ocean ridge genesis. And then Bain and Grove has a compilation of things that it's using. It's trying to update Kinsler and Grove. It's also incorporating experiments that have been done on variably metasomatized mantle or variably depleted mantle. And so it's trying to do a really good job at upper mantle melting that is dry, essentially, but could have variable bulk compositions. Whereas P-melts, if you think about it, P-melts, they use slightly different methods to regress the experimental data. And that might be a little bit of it, but probably the largest bit of it is if I'm trying to do a really good job of capturing a melt that was generated at 45 kilobars, as well as a melt that was generated at 100 MPa, right? I'm trying to do the best job, but I'm trying to fit a very large PTX space. Whereas with these, there's maybe a more limited PT range that they're trying to cover. So they're fitting a different experimental database, so to speak. I know, right? Well, I suspect that if you talk to different PIs in this room, you would get different answers. There's pros and cons to each model, right? So the question is, what is it that you're trying to solve, right? And I think that's where, and we're going to use not specifically these in a forward capacity, but in a thermobarometry capacity, like a reverse capacity. Like I'm going to take a basalt and I'm going to try to figure out what temperature and pressure it came from today in the tutorial. And you'll get to see a little bit of those sort of balances between, but it depends what your question is. Like what environment are you studying? What is the problem you're working on? Yeah.
Is it safe to say that everybody agrees at 10 kbar?
Yeah, 10 kilobars agrees much better than, it's here, for example, at the highest pressures that things are really different, you can see. And this is sodium versus silica and sodium versus iron, and I chose those because those show the worst fit. I didn't put up the ones that all perfectly fit because, you know, there's some elements in which they all agree great, but there is some ways in which they vary. So it's important also when you're looking at it, you know, you're working on a model to try to think about what is the elements or the things that I'm trying to reproduce the most, what are the most important to my interpretations, and so those are the ones you really are more beholden to fit. What we would love is to have one model that did them all perfectly, right? And, you know, but we're not.
Christy, along those lines, can you just say what Enki is and whether you think that will help?
Yes, so I have some slides in it for the tutorial this afternoon, but Enki, Enki stands for Enabling Knowledge Integration Development, I think it is, but it's really the name of a Sumerian god. And so Enki is this project sort of spearheaded by Mark Yorso and a number of other PIs, in which the attempt is to take all of the experimental data that exists and to digitize it and have it accessible open source so that you could go in and you could say, I want to, you know, use melts, or I want to use a melt version of melts, and I'm most interested in mid-ocean ridge genesis. So I just want to take that part of the experimental literature and data set that is relevant for that, and I want to use that to calibrate the model because that's what I'm interested in, and have that like best fit version. And the code will be all open source. It's going to be done with Jupyter notebooks and a Python platform, and so that anybody could go in and say, I want to pick this different data set as the calibration data set, and it would automatically calibrate the model for you with the data set that you chose, or you can use pre-specified ones that, you know, people have said this is a good database of experiments to calibrate your model for this purpose with. And it's also attempting to not only integrate liquids, so melts and solids, which is what melts is good at now. It's also integrating several other thermodynamic models like DEW, for example, which is the deep earth water model and looks at water speciation at various conditions. And also And also other solid water interactions like EQ36, where it's basically looking at equilibria between aqueous fluids and rocks. So the idea is that not only could you go in and say, I want this purpose, I want this, calibration data set, but I want to model the interaction between an aqueous fluid and a solid rock, or I want to model the interaction between an aqueous fluid and a melt or whatever. And so pick your phases that you're interested in. And so we're in a beta testing version of it now. Myself and some other people here are involved with the working group, and the goal is to have within, I think, 2 years to have something that's available to the public. So that's a good tool that's coming online in the future. The first thing that has to happen, though, is that we have to digitize the entire experimental database of experiments. And some of them have been digitized, but there's actually a lot of great literature that has not. So one of the things I'm doing this fall is we're having lock ourselves in a room and try to digitize a lot of data. So that is sort of one of the things that's sort of crucial to being able to do something like this. So this is just a cartoon to sort of re-emphasize that we do get a lot of dry melts in subduction zones and that a large range of that primitive samples that I showed you can be generated through, and we have pretty good models for this. I would say of the kinds of melting models that we have the best models for this. And the place where we're most likely to see that kind of that dry melting is in the upwelling limb of the corner flow, where we're having quite a bit of decompression of relatively dry mantle before it comes into the subduction corner here. And I touched on this in my lecture last week, but just to remind us, adiabatic decompression melting is when you have the mantle rising along an adiabat, and then it intersects the solidus, which has a shallower slope, and therefore it's energetically favorable for it to follow the solidus rather than to continue along the adiabat. And that difference in temperature between the solidus temperature and the adiabat is the heat provided, the latent heat of fusion to melt the sample. And so this adiabatic decompression melting is something that we see a good amount of evidence for in back arcs and even in continental arcs without back arcs, where we see some extension of the overriding plate. We see quite a bit of those make it to the surface. So now what happens if we add water? So now we're interested in, presumably, let's go to the simplest case first, where we have an aqueous fluid coming off the subducting slab. And here I touched on this last week, we're thinking about wet melting or flux melting, in which now any mantle that's along an adiabat, the solidus is depressed by the addition of water, causing it to melt. And there's been a fair bit of work on how much is the solidus depressed and to what conditions when we add water. So this is a very nice and important study by Hirth and Kolstad that looked at this. And so here we're looking at the temperature versus pressure for peridotite, and we have the dry solidus. And then what you see here are lines of constant water activity, which are in the dark black and dashed lines here. And actually, I think I have that reversed. The water activity is the dashed lines here. The black lines are lines of constant water content. And basically the idea is that you can see that when I add 10% of however much water it takes to saturate my mantle. Remember, when I add water, it's first going to go into vacancies and defects in my nominally anhydrous minerals. So I'm not going to have free water around as a phase. And when I do that, the first 10% that I add is going to lower the solidus this much according to this model, and in 10% increments all the way up till I've now filled up my nominally anhydrous minerals with water on those vacancy and defects. And I'm now going to saturate it, and then I would have the water-saturated solidus. So this is an important study that sort of laid out this sort of change in solidus based on existing experiments at the time. There's been a lot of experiments and a lot of attempts since then to sort of refine how adding a little bit of water changes the solidus, and I put a whole bunch of them up on this graph. And so here now, just to make life confusing, I've switched the axes. So temperature now, things are just sort of rotated 90 degrees. So temperature is going down this way and pressure is going up this way. And so here's my anhydrous solidus, and then we're adding varying amounts of water, and we're lowering the solidus. And so all these different models, so these are models for a constant water content, and then these are models for sort of lines of constant water activity. So you could think of those as I filled up 10% of the sites in my nominally anhydrous minerals if I have an activity of water of 0.1. Or I have filled them up 50% of the way if I have a water activity of 0.5. So we can see that there's different models for how the shape of these vary, right, a little bit. And this is another popular parameterization of the water-saturated, or addition of water to the solidus from Katz et al. That gets used quite a bit. I think, we can kind of dig into this, but the point is we don't really have one good model for how you depress the solidus as a function of water content. Different models have, again, slightly differences between them, and there's some that are easier to use, so they get used more often, but they don't always agree with some of the other models. And so, again, it requires some thought about which model you use and what its pros and cons on and what it was calibrated on. And we now know from also lots of experiments that not only does the addition of water change the temperature that it melts at, but we change the composition of the melt that is produced. So this is a study by Gaetani and Grove in 1998 that looked at the effect of addition of water on the melt compositions produced in major elements. And what we're showing here is this, essentially this is a reflection of how the liquid silica content changes as a function of temperature and how that changes as a function of water content. And so the samples that had been measured in dry melting were here, and the wet melting ones are here. So you can see that there's a different relationship between silica content and temperature for the dry ones versus the wet ones. And here we're looking at water content versus silica, but there's a clear relationship in this case where we can start to see that there's a relationship between the silica content and the water content in those melts. And so, sort of basically the explanation for this is we can think about when we add water that we're changing the silica to iron plus magnesium ratio of the melts, and compared to anhydrous melts. And this has to do essentially, it makes the hydrous ones elevated in silica compared to the anhydrous ones in this case. And really what's happening is we're lowering the iron and the magnesium content of the wet melts because those are a function of temperature. How much of them goes into the melt is a strong function of temperature. So because the wet melts are generated at a lower temperature, they have less iron and magnesium in them because of this temperature dependence. And so this is sort of one of a family of many studies that have shown how compositions are shifted as a function of water content in mantle melting. The other thing that we change is the melt productivity. So how much melt is generated for a given change in temperature or a given change in pressure changes when we add water to the mantle. So here is a family of experiments that are all anhydrous, and what I'm plotting here is temperature versus melt fraction. So essentially the slope of this line is dF dt. So the change in melt fraction is a function of increasing temperature. And so for the anhydrous experiments, we see a melt productivity of about 0.3% melt generated for every degree C that you raise the temperature. Now with hydrous experiments, what we see is a much lower melting productivity, about 1/3 the melt productivity. So you generate 0.1% melt for every degree C that you raise the temperature. And so you change the temperature of melting, you change the composition of melting, and you also change the amount of melt generated when you add water to the mantle. And this holds true in not only just where we think we have water being fluxed off the downgoing slab in the mantle wedge, but we see these effects, for example, in back arc basins. So there are these very nice studies by Katie Kelly and Terry Plank and other people who are here who show the effect of having water content here, looking at a bunch of back arc samples in the distance to the trench. And so basically the samples that are closer to the trench see sort of this greater effect of the metasomatism of the mantle, and that also lowers the melting temperature for these samples. So it's not just we can sort of segregate, oh, those are dry melts and those are wet melts, depending on where they are geographically. These effects have to be sort of considered across the melting environment of the mantle wedge, because we don't sort of laterally separate mantle that's been hydrated perfectly over time. So also, there's disagreement by, now once I add all of the water that I can add to those anomaly anhydrous minerals, and I've saturated them, so now I have a free water phase present, an aqueous fluid present in addition to my peridotite. What is the melting temperature of that? Because we think that is most relevant to maybe right above the slab, where the water is being dehydrated, whether it's from the mantle lithosphere hydrous minerals or whether it's from oceanic crust at shallower depths. What is the temperature of melting the mantle in that case? So this is a compilation of all the water-saturated solidi for mantle peridotite in subduction zones. And you can see there's quite a bit of variation. So early studies, Meeson and Boettcher in 1975 and Meeholen et al. In 1974 sort of set up the controversy that has continued. So Meeson and Boettcher found this very low melting temperature in the presence of water for 800 degrees. And this sort of is the pressure range where we're generating a lot of those primitive arc magmas. So they're finding that those can be generated at temperatures as low of 800 degrees, whereas Meeholen et al. Start finding that the melting only gets as low as 1,000 degrees C. And then more studies happened. So we had Kishiro in 1968 had already sort of established this at this higher temperature. Kawamoto and Holloway joined in 1997 and found a similar thing. Green et al. Had a very seminal study that is very well referenced in the literature that also agrees. So there's this whole family that have the melting curve at around 1,000. My PhD advisor, Tim Groves, did a study in 2006 at lower pressures, which I continued as part of my PhD at higher pressures, and we found that we actually agreed with these early studies. So Green came back and said, I want to revisit this, and came up with a new one that's over here. So, and then Smith and Asimov published one based on thermodynamic theory that's not based on experiments that does this. Okay, so where does this leave us? I mean, I could stand up here for an hour and talk to you about all the ins and outs of these experiments and why I think ours are right? But I'm not going to do that. But I am going to just sort of give you sort of what's the take home then, if it's one versus the other. So if you were to accept the Till and Grove and Meeson and Boettcher water-saturated solidus, the big implication is when you put it on a subduction zone, we have this range here of the altered oceanic lithosphere that's dehydrating, and the water contents that we've shown is consistent with triggering melting here in experiments at 800 degrees C for this range. So essentially, then you start melting the mantle, and you have melts that then rise into the hot core of the wedge, and because of the increased temperature in the hot core of the wedge, that melting extent grows, and you can get melting extents in excess of 10% melting in the hot core of the wedge. If you go with one of the lower temperature solidi, which would plot here, you have to have the water make it from wherever it dehydrates to here to trigger melting, which may or may not be a challenge. And then you would start melting here. So what would be predicted then would be that the extent of melting that you would get to in the hot core of the wedge would be lower. The maximum extent of melting that you would get would be lower because you had started melting at a higher temperature, and remember how I talked about how the melt productivity is pretty low when you add water. So we would not get in excess of 10% melting in the hot core of the wedge. So nobody's really tested that. So that could be a fun thing for you guys to test, right? Can we find a way to kind of test what the maximum extent of melting is in the wedge and prove one of these solid temperatures, right or wrong? But I will say that one of the things that probably, in my personal opinion, that's caused a lot of the controversy is just simply trying to do the experiments themselves. They were very challenging experiments to do, like I said, because when you have large amounts of water and you quench that experiment, you turn off the pressure essentially, it comes to the surface and all of the water that was in that melt exsolves. It turns into bubbles, and it makes the melt sort of blow up into a froth. I think I have a picture of it somewhere here. Oop, it's very much later, sorry. All right, well, we'll get to it later, but I have a picture of a froth to show you one of these experimental melts. And so not only do you have that problem, because then you have these fine little wisps, like these bubble wall shards, right? Just these coatings of bubbles of melt with which what you're attempting to analyze. So that's one strategy, because most of our analytical techniques make it very challenging to analyze this, like, hair of melt, basically, that we have. Then the other thing that makes it very challenging is when we talked earlier in the week about when melts are first generated at low extensive melting, they coat grain boundaries, right? And so they don't segregate into a big pool always in these experiments. So if we're really interested in where we first start melting, we're looking for places where we haven't melted enough that we've segregated a big pool of melt to one side of our experiment. We're looking at places where we have just melt coating those grain boundaries. And that can be very hard to identify in experiments. And it just so happens that where we see some other minerals break down, clinopyroxene and pyroxene coincides with where a lot of the solid eye temperatures are at. So it's basically the problem with the disagreements between these all lies in sort of the nitty-gritty details of the experiments, which is why it hasn't sort of been definitively solved. I'll just sort of advertise. We have a paper in prep where we've done experiments. This is the solidus from my thesis, and this is the green solidus, and we've done experiments sort of crossing all of these conditions with all these family of solidi and the newer green solidus. And we're looking at melt composition here. And remember, I said melt composition is changed by water content, but a question that we have to ask ourselves is, what is the very first melt really like, right? Not when you melt to high extents, but when you're having low extensive melting. And what we find in these experiments is that the melt composition, so here's temperature increasing, and here's the silica content of the melt close to the solidus, where we can first get a probe beam on it, which is about 925 degrees. These experiments, most of them suggest these silica contents are like 60. So we're firmly in an andesite field. And then as you get to higher extensive melting, then you get something that's more traditionally what we're familiar with, which is more of a basalt. And so actually at these very low extensive melting, we're getting something that's quite silicic. And it's that increase of extent of melting that brings it down to sort of lower silica contents. And also here we're showing temperature increased and the calcium content of the melt. And you can see that the calcium content of the melt at low temperatures is really low. But then we have a big spike in calcium content of the melt where we see clinopyroxene and garnet depleted essentially out of the residue in these experiments. And this is where the green et al. Solidus is identified. And it might be that it just takes that to sort of get up to higher extensive melting and to identify it with their methods. So the jury's still out, but you have my 2 cents. So we also can look at the melting reactions that happen with these kinds of experiments. So what minerals are being consumed in the melting reaction? What is the melt that's being produced in the melting reaction? And the coefficients on that melting reaction by looking at how the abundance of minerals, so this is olivine, OPX, The liquid is in yellow, garnet is in purple here, and CPX is in blue. So how are those changing as we increase temperature during the melting reaction? And so here we find in these that we're melting the olivine plus CPX plus garnet, and we're producing orthopyroxene plus melt during these melting reactions. And so we have a very similar, as we talked about earlier, this lower melt productivity is a function of water content. I'll get to you in like 2 seconds. And then a really interesting outcome of this is that the assemblage, the residue of this melting process is CPX plus garnet in terms of dictating the trace element budget. And so the trace element budget of this melting reaction is likely to be similar to something that has an eclogite residue. So that makes our trying to understand some of those signatures that we see in trace elements a really interesting component. Yeah, Michael.
Christy, on this slide, the previous one on the right, it says water, sodium, and potassium. Can you explain what that means and why it matters?
Right. So here what we've done is we have our bulk mantle peridotite composition. In this case, we're using the Hart and Zindler 1986 mantle composition, which is a relatively undepleted mantle. And we're adding 3% bulk water to it. So we're adding some water, but we're not adding like so much water to it. And we're also adding some alkalis with that, because we think that that mimics essentially the kinds of fluids that would be added to the mantle during subduction. And we're looking at analyses, or the best guesses that we have of the composition of those fluids, to add those, because the sodium and the potassium can affect things like the mineral stability and the melting reaction. So that's why we're choosing to do that. Does that answer your question? Yeah. Any other questions while we're here? Yeah. Yeah, so these ones were all at 3.2 GPa. This set that I'm showing you here. So that's sort of the maximum sort of range. If we go back to our cartoon of a subduction zone, 120 kilometers depth maybe, sort of the maximum depth below arcs essentially that we see depending on slab dip for melting. Yeah.
Does the melting itself generate heat and lower pressure?
Can you say that again? Sorry.
Does the melting itself
generate heat?
generate heat or lower pressure?
So there's energy required for the melting process to happen. That's what we call the latent heat of fusion. But here, essentially, the melting is produced by this addition of water. And so we are not generating heat with this melting reaction. Pardon me? Yes.
Okay.
And then your other question was overpressure. Yeah. So this, for example, so if we have a melt in our experiment at the pressures in the device, it has all of the water dissolved in the melt. And then in this case, because we're water saturated, we have a little bit of aqueous fluid around, okay? And then when we depressurize it, that water exsols, right? And so it could generate a little bit of overpressure, but the amount of overpressure that it generates is so small that it's not like we blow up the capsule or anything like that, but you would generate a little bit during turning it off at the very end of the experiment. Okay, good questions. Any other, yeah? Oh, microphone's coming to you.
As the solid melt, the volume changes, right? So I'm wondering what kind of pressure sensitivity you can actually measure in your experiment. Is there a lot of pressure changes associated with the melting process, or does it stay constant?
Right. So the pressure in our experiments is generated by a solid medium. So we have this pressure vessel essentially that's providing hydrostatic pressure to it during it. So it's sort of the pressure, any pressure variation that you would be seeing would be on an extremely local scale within the experiment. It would not be the sort of pressure that the experiment is experiencing overall. Does that make sense?
The melting is very localized. What happens?
pressure change will be inside the sample, but your pressure vessel is large
Right.
in comparison. And so the friction and so forth control the overall pressure. But inside the sample, how do you tell how pressure changes?
Well, so we have, I mean, the way that first of all, when we calibrate experimental apparatus, we look at experiments or reactions that have known pressure transitions, right? And so we calibrate all of our apparatus to know when it reads this on the dial, this is actually the pressure the experiment's seeing. And we can use that to account, when we do that, we understand what the friction corrections are, or if there are any, for the particular device or apparatus. When we're doing the experiment is positioned in a number of buffers, or like a bunch of different solid media, some of them are made out of MgO and aluminum and things like that. And we know that their relative behavior during the pressure changes that they experience. And all of that stuff is sort of designed such that there shouldn't be any pressure fluctuations essentially during that, and if there were, we'd be able to tell by when we took the experiment apart essentially. And oftentimes, if there is a significant change in pressure for some reason, then the experiment will fail because the contact of the thermocouple will stop touching the experiment and measuring temperature. So any volume change we can look at using the Clausius-Clapeyron curve of our solidus to understand the relationship between the volume change between the crystals and the formation of melt, right? And we don't see sort of any addition of anything else, and we can kind of, so I guess I'm inferring that the volume change that we're getting is very small at pressure. That's not doing, we're able to constrain if there were any large volume changes. Okay. I'm happy to talk to you more about that offline. I can show you some of the more specifics. All right, and on to the questions. All right, so if we go back to this Miyashiro diagram that I started with, we sort of looked at these as a product of variations in the dry mantle melting process. And we can look at these as compositions that we can produce through variations in that wet mantle melting process. So things, for example, I showed you those first melts maybe of the very wet mantle, the water-saturated mantle. Some of them had silica contents way up here. And we see this higher silicon ratio that's a product of adding water, just like Gaetani and Grove showed, relative to iron and magnesium contents. And we can see variations within this field as a function of the extent of melting. So this might be lower extent meltings, and higher extent melting actually move us this way, as long as we still have a Lherzolite residue. If we change the residue now, if instead of having a Lherzolite residue, say we're melting Harzburgite or Dunite as our peridotite, then we actually have compositional shifts in the melt that is produced too that have been experimentally investigated. So I went back to the same ternary space just to show you that melts of a Lherzolite residue, or if you think about what makes up plagioclase, right? Sodium, potassium, aluminum, silicon. These elements are relatively higher in the melts that are produced from a Lherzolite residue compared to a Harzburgite residue, which remember is just olivine plus OPX. And the Dunite residue here has the most depleted in those. So we can actually use the compositional variation of the melts to also infer something now that we've experimentally calibrated these spaces, something about the residue that was melting to form them in major element space too. So if we go back to this diagram here, Harzburgite melting, this diagram doesn't include the alkalis, for example, and things like that, but Harzburgite melting also takes us off in this direction. So increased Harzburgite melting or depletion of the residue will take us off in this direction. Oh, I added that here. So here's this Miyashiro diagram again. And so here's things that are sort of wet mantle melting, and increased depletion of the residue will follow this gray arrow over in this direction on the Miyashiro diagram. So we can start to explain a wide range of the primitive basalt compositions that we see in arcs by these various melting mechanisms of the dry, the wet with the different residues, the wet with the different extents of melting. And then, of course, we have the additional complication of variations in the thermal structure. So those might be things that cause changes in the temperatures and water contents of melting. So I'm putting up our nice figure from the paper with Peter that shows here for a much colder subduction zone, the water content as a function of depth, the lithology as a function of depth with the key up here, and moving towards a very warm subduction zone like Cascadia, and the water as a function of depth here. So now, in addition to sort of just looking at systematics in residue composition and extent of melting, we can sort of ask some of these questions about the thermal effects and water content effects. Here I took a suite of primitive basalts that have been relatively well studied, and I plotted them up by their region. So these are different arcs around the world that they're from, on that same Mioshier diagram for consistency. And it's kind of hard to see because this big orange cloud of cascades sort of drowns it all out, but there are quite a bunch of Isobone and Marianas samples that are behind it. So what we see also, though, is that there's regional variability. Not all arcs are producing the same primitive magmas, or the relative proportion of primitive magmas are different at different arcs. So here at Isobone and Marianas, we're seeing a little bit more of these wet ones that sort of go off in this direction, whether it's to very water-saturated melting or melting Harzburgite. And then in Cascadia, we're seeing a little bit more of these anhydrous ones, those dry mantle melts, and a little bit less of whatever is driving the higher silica content for the Isobone and Marianas. And that's not surprising considering those thermal structures we were just looking at, right? So higher water contents available to greater depths because of cooler temperatures compared to Cascadia, which might have a greater relative proportion of this anhydrous melting. So, and then there's other arcs in here. We have some Japan samples here, for example, some from Mexico and the Andes here. So we don't have, on this particular plot and samples that had been well studied, we don't have a representative database from each arc, although more work can be done with some of the published literature to try to understand it and really get back to these primitive melt compositions and see if we can sort of tease out more global variations. But where we have a lot of data, both from Cascadia and from Isobone and Marianas, we can sort of see some trends that we would expect in the data. So I talked about how we had forward models for melting of the dry mantle, and that they worked pretty well, but there were some problems with them. Well, models for forward mantle melting, i.e. I want to specify this temperature, this pressure, this bulk composition, and this water content, and I want you to predict the melt composition for me, those are much more in their infancy. We have some models. So this is a compilation that I made of trying to show how the melt composition changes as a function of water content. And you see that we really struggle at the sort of lower water content. So this is looking at, here I'm using, because I'm a petrologist, apologies, mineral component space to show you vectors and how the melt composition varies. But just basically suffice it to say that in any one of these, this is the experimental data, and it's not a clear fit, right? That how the quartz component or the plage component of the melt composition changes as a function of water content is very messy, and that's largely due to not having very many experiments that do that very well, and also having experiments that are drastically different. And then, so this is something that begs more work. And my student, Megan Guild, had some information about sort of attempting to do a better job of this on her poster last week. And recently there was a paper on Harzburgite melting by Mitchell and Grove, which does a very nice forward model of melting Harzburgite, and also shows that it's quite a nice fit for a lot of primitive andesites that we see globally. But so there's a forward model now for Harzburgite melting, but that's really where we're at. If you really want to understand major element compositional variation and you want to change variables like, you know, temperature, pressure, water content, bulk composition, we don't have a good model for that, one model that does that at this point. There's the slide I was going to show you. So here's we're looking at, and the reason why we don't have these models yet is because of how hard the experiments are. And so this was my attempt to show you that. So this is a picture of one of those quenched melts in an experiment with water, such that it exsolved during its degassing. And so these are these little bubble walls, essentially, that are left of the melt. So that's what we have to analyze. And so this is a cartoon to sort of help you think about what has happened here. Here's another image of another experiment. And you can kind of see that they're sheets in 3 dimensions, but since we are taking a 2-dimensional slice through it and trying to analyze it, it's very challenging to measure these bubble sheets that are the outside of the bubbles here. And so this is sort of the experimental challenge with developing robust models for this sort of water-driven melt.
Simple question, why don't you quench it at pressure?
So we do this. There's a method called a pressure quench where we can, and we get less of this, but we still get it. And it's also that the water promotes, so you think about the water is essentially anytime you have the tiniest bubble, it provides a nucleation site to grow quench crystals. Essentially, we get rapid growth of sort of metastable crystals during the depressurization process, no matter how quickly we quench it. So with the pressure quench works pretty well at low water contents, so when we have only a dissolved weight % or less in the melt. But as you start to get to higher water contents, there's essentially, we still can't prevent, just with the sort of speed of humans turning off everything and pressure, turning off temperature and pressure, you can't prevent these tiny sort of submicron bubbles forming, and we promote quench growth. So either so you get less of the frothing of the melt, but you still have growth of quench crystals at the higher water contents. Yeah.
What is the quenched fluid relative to the quenched melt?
Yeah, so this is, so when last time we talked a little bit about, during Paul's talk and during my talk last week, we talked a little bit about this idea that, when you're at high pressures, you can have a lot of solute dissolved in your aqueous fluid. And we also have this question of what we call the second critical endpoint. So above what conditions can we stop telling the difference between a silicate melt with a lot of water dissolved in it and a aqueous fluid with a lot of solute silicate material dissolved in it? Those become one above a certain condition for a given compositional system. And so there's been questions about where that second critical endpoint is for these systems, these peridotite water systems. And I think we have pretty good evidence essentially that our system had a high pressure fluid that had a solute dissolved in it, and we had a high pressure melt that had water dissolved in it, because when we quench these, we have the quenched melt, but we also have these spheres of solute essentially that have essentially all the things that were dissolved in the high pressure fluid phase in them that are a very different composition from this. So we think we had a 2-phase system at high pressure. Yeah. Microphone. Yeah.
The space between the melts are colored black, right?
Yeah,
these...
this is epoxy that has been impregnated into these so that you can sort of not have them fall apart and analyze the composition of these.
I see. So there's a lot of space that is filled by epoxy in your sample.
Right, and so presumably at high pressure, we had a bubble here, when we were depressurizing the experiment, we had a bubble here, which is now gone, and that's why there's this solute bleb here and this wall of melt material around it. And you can imagine that at higher pressures, we had a more continuous melt that was not broken up like by the bubbles, like down here. Okay. So,
sorry, Christy, just quickly, you have 15 minutes.
Yeah.
But you've had a lot of questions.
Right, that's all right. I'm pretty near the end. I just wanted to touch on, a lot of what I focused on so far is the idea of adding simply an aqueous fluid from the subducted slab, and we've had a lot of discussion so far about, well, what if the flux from the slab is not simply an aqueous fluid? What if it's a melt of sediment? What if it's a melt of oceanic crust? So I just wanted to touch on a few of those things. So we had this nice example of a study during Paul's talk from Christina Wolowski's PhD that looked at compelling evidence for melting of, in Cascadia, melting of the oceanic crustal portion of the slab using up-to-date thermal models of the slab structure and where we'd expect to get the dehydration of the mantle lithosphere. We still have water being released from chlorite dehydration, but we would have lost all the water and then be above the melting temperature of the oceanic crust here. And so that's compelling reason to think we could look for that. And when we do experiments on melting of eclogite or melting of metamorphosed oceanic crust, we see that that melt composition is quite different from the melt composition that we get when we melt the water-rich mantle or when we melt the sediment, for example. So the compositional variation shown here, so this is temperature increasing versus weight % silica for a study that's looking at melting eclogite, water-rich eclogite. And you can see that at low temperatures, the melt that is generated by this study is above 75 weight % silica at low extensive melting, and as you get up towards higher extensive melting, you get down to 60-some weight % melting. So the aluminum content also changes quite a bit. And so this is just to sort of discuss this idea that if we really do have a flux from the slab that is something other than an aqueous fluid, the composition of those first melts that are produced in the base of the mantle wedge and then rise up and react with the mantle are quite different depending on what you think the melt was. It was if it melted the mantle, melt of sediment, melt of oceanic crust. And so these are ways that we can start to think about testing some of these models, which Christina did in this paper where she took took the experimental melts that I just showed you and mixed them with the mantle to try to say how could they reproduce or could they reproduce these Lassen melt inclusion compositions of primitive melt, and they're a pretty good fit. I will note, though, that this is using p-melts, right, to compare the melt composition. And so, the models are quite good fits and all that kind of stuff, and it might be worth asking in some of the element spaces, like the alkalis, how do those vary with different models? And also their studies showed quite a good fit for the isotopic composition of the Lassen melt inclusions when we compare them to what we expect for the addition of the slab melt component to a mantle component with some sediment influence and how that fits them. And so I think this is a nice example where we've looked at a case where there's major elements examined, trace elements examined, isotopes examined, all internally consistently to try, in contrast with what we thought from thermal models, to all try to explain this evolution. And so I think, for the future, that's something that we really need as a community to ask ourselves to do, which is not take one of them, but to take all three of these different kinds of data sets to integrate them. And there are places and studies that have done this, but we don't sort of systematically do it as a whole. And that's because it's really hard. And what it requires is us developing forward models for major elements, predictive models for trace elements, and predictive models for isotope behavior through the entire subduction system, essentially from the slab to the surface, and integrating that history, which is a really hard thing to do. But I think we're getting closer to a place where we can start to try to do that, and that this is a real opportunity for advancement in the subduction zone science community to try to integrate those histories and not just look at what we think might be the signature from one part of the system. I'll skip this for now. So just going to kind of wrap up and go back to what I started with, which is the question of, I showed that nice view from the 1990s that was like, are we melting sediments? Are we melting slabs? Are we melting the mantle? And I showed this slide the other day, and I think we're still asking that same question today. We have these nice thermal models that show us that it's very reasonable in these worm subduction zones to be melting sediment and or oceanic crust. And then we have these colder subduction zones where we have very strong evidence that we're melting the mantle in the presence of an aqueous fluid. And so it's probably not just one. It's probably all. And the question is, can we identify, how well these thermal models are predictors? Can we go and look in specific places and see the difference between something that's a product of taking that oceanic crustal melt and then integrating it with the mantle as it rises to the surface and erupts, versus taking that mantle wedge melt and integrating it with the mantle and then having it erupt? Can we actually tease out the difference between those two things in all sorts of element space, and see the difference, rather than sort of doing it more qualitatively? And this is just to hit home the point that when that melt, whatever it is, if it's oceanic crust, if it's sediment, if it's mantle wedge that is formed here, when it rises, it interacts with the mantle and it changes its composition, it changes its temperature. So this is a phase diagram here where I have percentage water versus temperature. And at the first, we're going to follow two sets of lines. The green ones are sort of P1, so imagine we're down here. Okay, and so we have a lower temperature, and then the melt rises up, and now it's in this condition of the red lines, so it's in a higher temperature in the hotter core of the wedge, and this melt is now out of equilibrium with the phases. It should be on this red line here, which is the boundary between crystals and liquid, and so in order to get there, it has to grow in melting extent, essentially, and lose bulk water content. So by increasing the melting extent, the relative proportion of water is decreasing, and then it ascends and keeps repeating this process. So as the melt rises, it comes to thermal equilibrium with the mantle. We think it comes to chemical equilibrium with the mantle. That melting extent rises. So anything that's generated here has to go through that process before it can get up to erupt. And so it is going to then have this sort of reaction process that changes whatever its fundamental character is. And I skipped a slide that showed, we have to consider how that changes the trace element budget, as well as how that changes the major element and isotopic budget as it rises. And we have quite nice evidence that these melts then do that they rise, and that they sort of stagnate, or they're last in equilibrium with the mantle at the depths right below the lithosphere-asthenosphere boundary. So this is a nice study that came out recently by Planck and Forsyth. This is doing this for a suite of primitive basalts from the basin and range. So not in a subduction zone setting, but they're showing you the essentially the last conditions of equilibration of all of these primitive basalts right below the lithosphere-asthenosphere boundary. And we can do this in arcs as well and see that even all these different types all reconstruct to depths right below the lithosphere-asthenosphere boundary. So all of them are showing this evidence of that thermal and chemical re-equilibration as they rise through the hot core of the wedge. And so we can't sort of escape the effects of that prior to their eruption. And there might be some nice reasons for that in Cian's models, where you sort of see this sort of ponding, perhaps, or a location where you see a lot of things focused into certain areas. That might be one reason for that, but there's certainly lots of work to be done on the sort of rheology and geodynamics of how these fluids and melts flow through the mantle. And I'm going to skip this and just finish up in the interest of having time for questions. So in a simple sort of Occam razor's view, a major element view, we can explain a lot of the geochemical diversity of the things, of these primitive rocks that we see erupted at arcs, by wet melting of the mantle and dry melting of the mantle, and of different residue compositions. Yes, there's probably some places where we have sediment melting and oceanic crust melting. And yes, we probably have places where we have very changes in extensive melting because of changes in water fluxes. But sort of as an average integrated, simplest explanation view, this is one. And I already talked about how now, if we go back to this, I think the answer is, all of these things might be important, and not just one of them. And so opportunity, I've said a lot of this already. I think future opportunities include integrating, experiments and thermobarometry of natural samples, are to the point where we can sort of reconstruct where these things were the last time they were in the mantle. And the experiments and the modeling I showed you tell us a lot about how they're generated at the base of the wedge. But the opportunity for advancement is really an integrated history from slab to surface for these kinds of samples that track major elements, trace elements, isotopes, and that we really do need to continue to work on in order to do this, our forward models of melt composition as a function of all these variables, and in particularly in the presence of water. So I'll leave it there.
Student and postdoc questions first.
Yeah, for the disagreement you had between the water-saturated solid eye in the different experiments, I was wondering if some of that might be because some of the experiments weren't water-saturated. You're running these experiments for a long time at high temperature to have equilibrium, and water diffusion can happen through the capsules. And so I was wondering if, how well we know what's happening with water in those experiments.
Right, yeah, it's a great question. So for all the experiments that I did for my thesis, for example, we spent a lot of emphasis on trying to make sure that we had the same, we didn't have water loss, that we were using gold capsules, and we looked for them still being water saturated at the end, right? So we would drill a hole in them and make sure that there was a free fluid phase that came out that indicated that they remained water saturated. And then you do mass balances for elements to make sure that they haven't had any iron loss or water loss when you do the mass balance at the end. So with those, we're quite confident. Now, when you look at the literature and you go back to some of those older studies, some of the stuff from the 60s or 70s, it's harder to tell. Although they seem to still fall in the same two families of solid eye. I think some of the Kawamoto and Holloway ones, it's pretty clear. So a lot of it has to do with how were the authors identifying melt in their experiments. So Kawamoto and Holloway pretty much explicitly say, we were looking for a pool of melt, and we were using refractive index oils to do that. And so in that method, it's going to be, it's a lot harder. You have to have a higher extent of melt to see the melt. Whereas in other studies where you have electron microprobe to be able to do nice SEM images and all that kind of stuff to identify melt, then you have an easier shot at seeing little tiny wisps of melt and things like that, coating grain boundaries. And so I do think the question of some of the early experiments were done in graphite capsules where there was most likely water loss, but then as time went on, the experiments were done with more and more robust methods. So they're, pretty comparable in some ways. Yeah, but it's true. You have to when you do experiments, sort of every detail of the method turns out to be important. So you read those parts with a fine-tooth comb. Yeah. I think there was one back there and then over there.
Yeah, so we've talked a lot about how the chemistry of these melts can be very different in different conditions. Yeah. To what extent does the viscosity of the melt also change with these conditions? Mm-hmm. And does that produce different sort of migration patterns, whether or not it's hydrated, right, so on and so forth? Right.
Yeah, so there's a well-known trade-off between, so we see some of these hydrous melts having higher silica contents, right? So they're going to have more of the network-forming silica, so that's going to increase their viscosity, but then we also know water decreases their viscosity, so there's sort of this trade-off between those two. So there's, this is not something that I'm an expert on, but there is, literature that looks at how the viscosity varies. And I think the question of has that been integrated into sort of, say, dynamic models of melt flow is a great one. I don't know if there's anybody in the audience who can answer that question.
Yeah. What was the question?
The question was, there's going to be variations in melt viscosity as a function of silica content and water content, and has that been incorporated into any sort of dynamic modeling when we model fluid or melt flow?
Not that I'm aware of. Certainly my models just incorporate that into a single mobility parameter, which is like the ratio of the reference fluid velocity to the reference solid velocity. And you would need to dynamically incorporate it into that somehow.
Yeah, so something to work on.
Can you show that diagram of the controversy between the green experiments and your experiments?
Yes, I can.
I have a question about the clap around slope. I think it might be easier if we look at it.
Everybody loves a good controversy, I guess.
So you said the Smith and Asimov was based on thermodynamic calculation.
Yes.
So is there a reason that their slope, because yours is just going straight up after 3 GPa, and theirs is a positive.
Turns over, right. So if you think about the Clausius-Clapeyron equation, essentially what you're looking at, there's a balance between the volume change, right, as a function of temperature between the products and the reactants, like so on what's on either side of the boundary. So here we have crystals, and here we have crystals plus melt. And if we assume that the crystal's volume change isn't significant, then essentially what you're looking at is the volume change that has to do with the addition of the melt. And so what they're predicting is that so where that curvature is here, right, or here, depending on which one you look at, they're essentially the slope, or the change in slope, the second derivative there is 0. And so what you're looking at is a place where there should be no difference in, here there's a positive difference, and here there's a negative difference. All right, maybe I have that reversed. Negative difference and a positive difference in the volume change. So essentially you're looking at a change in the relationship of the volume change of the melt, like when you have the melting process. And so they're predicting that that turnover is, at very low pressures, less than half of a gigapascal. So in most places this would be in the lithosphere. And so it's not super relevant for wet melting of mantle peridotite, whereas these predict, you can see these are starting to turn over, that volume, that second derivative equals 0 at a higher pressure. Which one is right? I mean, there's some other reasons why we don't really see evidence for this in nature, but whether, where it turns over and how we can test that in nature is a good question.
So we'll take one more question and we'll open up to everyone now.
You mentioned that overall the picture is that there's reaction as the melt ascends through the wedge, and that equilibration of the melts as they're ascending. I was just wondering whether you wanted to comment then on the time scale of the transfer of the melt from initiation of melting to eruption, in comparison also to, for example, uranium series models,
right,
and also the melt fractions that are implied
by
both.
So there's lots of people who have started to think about this. Let's see, where is my slide? I have a slide to help us here, if I can find it. Oop, I think I hit it, so it's not showing up here. Yeah, so constraints from U-series require that, well, there's a variety of constraints, but the constraints require that the melt essentially make it from its point of origin to eruption in less than 10 to the 5 years. And so this is a model comparing Stokes flow versus porous flow. So this is the radius of the diapir in Stokes flow versus ascent velocity. And then here for porous flow, this is sort of reaction time. And so here in this model, in order to have, so this is what we predict with Stokes flow, and the thermal reequilibration of any diapir that's, let's see, we have diapirs here. So this is 1.5 kilometers of the radius of the diapir. We would have thermal equilibration of it in that time. So in order for a diapir to make it to the surface in the time scale required by U-series, it has to be very large, okay? according to these calculations, which is from, I didn't put this up here because I didn't end up using this, but Grove et al., 2002. And then here, we also need to have an ascent velocity, even if we have porous flow that's fast enough that the melt doesn't just get dragged down by subduction. And so in order to have an ascent velocity such that the melt doesn't get subducted, and the calculation here is greater than 5 times the subduction rate. So that's here. And so you have to have flow velocities that are sort of in excess of 100 centimeters per year in order to prevent subduction of that melt. So you kind of have a trade-off. There's compositional constraints on whether or not we can have channelized versus porous flow, and I didn't go into them for interest of time, but most of the calc-alkaline samples, so those that look like they've been generated in the presence of water, we can't reproduce their compositions, and their sort of temperatures and pressures require that they reacted with the mantle during ascent. They reached chemical and thermal equilibrium with the mantle during ascent. And so they require a model more like this, and these kinds of ascent velocities. Some of the primitive basalts that are dry, they're a little harder to tell. You can fit them with a model where they have channelized flow, but it's a little hard to reconcile. You know, those channels have to be pretty big in the mantle, or you can do them with some reactive flow because they're generated so much shallower that the distance that they would have to go through the reactive flow is so much smaller. But in general, their paths, their temperature curves correct back to not that different from adiabatic, and so they seem like maybe they have more evidence for channelized flow.